Hey class, and welcome back to Chapter 9, Part 2, or Part B, where we're going to continue our discussion of rotational dynamics looking at Newton's second law as it applies to rotational motion and introducing a new concept known as a moment of inertia. So first of all, I just want to talk briefly about center of gravity. We talked about center of mass already back in Chapter 7 quite a bit. For most intents and purposes, for things near Earth, center of gravity and center of mass will be the same. But if you recall, center of mass is, as the name implies, the central point about which all the mass is balanced. Center of gravity is the central point about which all of the forces due to gravity are equal. So if you think about like the center of gravity for the moon as a result of the Earth, all right, that might not be the exact same as the center of mass of the moon, because the near side of the moon is closer to the Earth and therefore is experiencing a greater gravitational pull than the far side is. But if it's uniformly distributed, the mass, then the center of mass would be pretty much at this geometric center of the moon, approximately. So yeah, the center of mass and center of gravity for most applications we're going to be looking at are the same, but center of gravity is really closely related to rotational dynamics and understanding torque and different things, and so that's why we introduce it to you here in this section. If you have a uniform object, then the center of gravity will be at its geometric center near Earth. So if you have like a cube or a sphere or a cylinder or a disk, then this geometric center will be its center of gravity as well as the center of mass anywhere near Earth's surface. And it's really just for very large astronomically sized objects that you'll typically be experiencing center of gravities and center of masses that do not line up. But the center of gravity is calculated in the same way that the center of mass was calculated, but instead of mass we actually have the weight, and so you're summing up or adding up different chunks of mass at their different distances away from some central point. And then dividing them by the total weight to get that location, just like we did with center of mass. So I'm not going to spend much more time here since we've already kind of dealt with center of mass. Now what I want to do is I want to look at understanding and thinking about Newton's second law as it applies to rotational motion. So let's imagine you have a kid here who's holding like a string tied to a propelled aircraft, or like, you know, like a little wind-up airplane or something. So the Ft here, it's not the tension in the rope, it's the thrust. So there's a thrust force forcing the airplane forward. So since it's being forced forward and it has a mass, then it will experience a forward acceleration as a result of that thrust, right? Now, how does that relate to any sort of torque that it's experiencing, since it's also going through this rotational motion? That's what I want to look at. Well, we know torque equals force times lever arm. In this case, that force is perpendicular to this radial lever arm, radius of its circle, labeled r here. So the torque, and it's counterclockwise, is just a positive, that force times the lever arm r. Okay, so torque is m times a multiplied by r. Looks good, cool. Now we know that this acceleration, since it's in the forward direction and it's tangent to the direction of motion, it's a tangential acceleration for the circular motion. We know back from last chapter that tangential acceleration is r times alpha, so we can plug that in. And what we find is that our torque equals m times alpha times r squared. Rearranging that, torque equals mr squared multiplied by alpha. Okay, interesting. So for Newton's second law, we had force equals mass times acceleration. Now we have a similar pattern. Torque equals this thing times acceleration. And that's a pattern I want you to really notice. I want to take a second and show you this on the board. So think about our different equations that we've been looking at and learning from all semester. I won't write all of the equations of motion, but you know, we had, for example, final velocity equals initial velocity plus acceleration times time. We took that equation and then we redid it in rotational motion, and it became the very same. Omega equals omega initial plus alpha times time, right? You're going to see this pattern of having the same equations in linear motion and rotational motion, where the variables just change from rotational to linear, but they look very similar. So for example, now what we're about to discover is we had net force equals mass times linear acceleration, and now we're going to have net torque equals, instead of mass, we're going to introduce this new term known as this new term known as the moment of inertia. So I represents inertia. So mass is sort of equivalent to the amount of inertia something has for linear motion. I is the inertia when trying to rotate it, okay? And then multiplied by alpha. And we're going to keep going with this idea. If you remember kinetic energy, that's 1/2 mass times velocity squared, right? Guess what rotational kinetic energy is going to be later on in this chapter? Well, it's going to be 1/2. Instead of m, we're going to have I omega squared, and continuing on. We even have, remember we had momentum equals mass times velocity. We're going to have angular momentum equals I times omega. All of our things that we're learning, we're now seeing very similar looking equations for rotational motion, all right? So keep that in mind as we go forward. We really are going to be seeing this pattern more and more. All right, so that's the idea of torque, and this is true for, again, individual objects or systems of objects. And this value here we call the moment of inertia. Now, m times r squared is the moment of inertia for just a point mass, one single object at some distance r away. If you have like a more complicated object, you know, like say I wanted to spin my calculator because that's cool, right? Its moment of inertia is going to be more complicated because it's a rigid body with a distributed mass, which we'll talk about here in just a little bit. So that was for a single force acting on a single object. If you have multiple torques acting on multiple masses, you really just have to add up all of the mr squareds for all of those and all of the torques to figure out the net acceleration of your whole rigid object, okay? So to do this really to any meaningful degree, you really need calculus. You're going to integrate over these different things, but this isn't calculus-based physics, so we don't have to worry about that. But if we're thinking about, you know, like, hey, here's my phone, I'm going to hold it at one corner and let it drop. What is its angular acceleration going to be? Well, it's really, there's a torque acting, you know, on this sort of chunk of mass right here, and there's torque from this chunk of mass and this chunk of mass and this chunk of mass. But each of those have different R values, so they have different inertia and different torques because they're different distances away. And so you'd have to sort of add up all of those little pieces together to figure out just the phone. But I'm going to give you some tools of how we can simplify that idea. But again, net torque equals moment of inertia multiplied by angular acceleration. So again, this is Newton's second law, 2.0. Net torque equals moment of inertia multiplied by angular acceleration. Keeping in mind that for individual point masses, the moment of inertia is just all of the m's times r squared, which we'll do an example of here in a second. And for more complex objects, you need calculus, and I will just give you some of the solutions that calculus has shown us so you can use those. All right. Keep in mind also physics is rad, so angular acceleration should be in radians per second squared. All right, so here's an example. This is kind of interesting to think about. You have the exact same object. All right, you have two equal masses m on either end of a rod L. So imagine, you know, this is your rod and you have two masses, one tied to each side. I can look at this, all right? So I got one object here with two masses, one on either side. My question to you all then is what is its moment of inertia if my axis of rotation is at one end? So I'm swinging it, I guess, let's call this my axis of rotation. So this side's moving, all right? What's the moment of inertia with that setup? And then what's the moment of inertia if your axis is in the exact center, and so instead you're moving it about that central point, okay? Which do you think is going to have more inertia? Which is going to have more resistance to rotation? Again, inertia is a resistance to change in motion. So mass is your resistance to change in linear motion, and moment of inertia is your resistance to change in rotational motion, okay? This is the idea, like, I used to play baseball, right? If you hold a baseball bat at the handle and swing it back and forth, it's much harder to rotate than if you flip it around and hold the barrel and do the same thing. Same object, same mass, different resistances to rotation based on how that mass is distributed. So what about here? Pause it, try it out. Calculate the moment of inertia in both setups. Ready, go. All right, so let's do it. Again, moment of inertia is m times r squared added up for each mass. So if we start in setup A, you have m1 times r1, which since the axis runs through it is 0, plus m2 times L, the length, which is R2, that's the whole length of that rod, squared. So since the m's are m, you have m times 0 plus m times L squared. Your inertia is ml squared. Cool. Now let's go to B. Do you think it's going to be the same, more or less? Well, check this out. You have m times, now both R1 and R2 are both half the length of that rod, right? So L over 2. M L over 2 squared plus m L over 2 squared. L over 2 squared is L squared over 4, right? So you have basically ml squared over 4 plus ml squared over 4. You add 1/4 plus 1/4, you get 1/2. Look at this. In this setup, taking the exact same two masses on the exact same rod, rotating them about this axis, cut your inertia in half from ml squared to 1/2 ml squared. So just changing your rotation from down here at the end to here in the center with two masses on either end, cut your inertia, the resistance, in half. Pretty weird. If you don't believe me, try it out. Grab something with masses on the end and wiggle it around. You'll see. So again, ml squared is for point masses. When you have rigid objects, more complex objects, things like spheres, cylinders. So here, like you see down here, a solid sphere, think like a baseball. A hollow sphere, think more like a tennis ball or a ping pong ball or something. You can have solid cylinders. You can have thin-walled cylinders. You can have hollow cylinders. Some people are like, what's the difference between this and this? Well, really, you can use this equation for actually E through F, or E, F, and G can all be summarized with this one equation. But this is just a simplification. If it's super thin, the inner and outer radius are approximately the same, and so this just becomes mr squared. You can have rods, you can have rectangular solids. This here, right, rectangular solid with an axis at one of the edges, that's basically just a door, right? Okay. This here is like my phone. If I'm rotating it an axis through the center like this, that would be for C. Okay. Now if I took the same phone and rotated it like this, that would be in D. Now notice I can rotate my phone like this, right? Or I can turn it and rotate it like this on this axis. Okay. Those both have different inertias because in this way, my axis is on this edge, and so the amount sticking out is a shorter distance, labeled A in that picture, right? Whereas if I turned it this way, I now have a longer distance, and so that gives me a different moment of inertia. So you got to think about the geometries. This list, though, this is pretty useful. I'll try to remember to give it to you on quizzes and things like that, but on homework and stuff, it's not going to be there. So I would recommend either writing these down on your equation sheet, or even some people have just like printed this out or even just taken a picture on their phone and just had their smartphone with them. But I would recommend just writing them on your equation sheet because you can't use your smartphone on the quizzes and tests and things, right? But these are different geometries, and you'll see some of these as we go forward. Okay, so now what I want to do is I'm actually going to spend the rest of this video just doing some kind of simpler examples, and you can look for more complex examples on Foxtail as well. Okay, so here's the first setup. You have a yo-yo. You're going to just hold it on one end, and you're going to let it go, and it's going to rotate down. My question to you all is, what's the acceleration of the yo-yo, and what's the tension in the string? Some of you want to just say, well, you're dropping it, its acceleration is 9.8. It's just g, right? Meters per second squared. No. Believe it or not, because it's rotating as it moves downward, it's actually dropping and accelerating downward at a slower rate because of that need to rotate. Because some energy is causing it to go into rotational motion, you are actually going to see that it accelerates less than the acceleration due to gravity. How much less? I want you to figure it out. Some of you also want to think you're holding the string and the object is just hanging on there. So you just think that the tension should be equal to the weight of the object. Since it's accelerating downward, it's not. It's less than the weight of the object. How much less? Well, try it out. So follow the same procedure. Pause the video, draw yourself a free body diagram, and then start going through some of the forces, some of the torques kind of stuff. All right? Ready, go. Hopefully you did it. Here's my free body diagram. So I draw my yo-yo. My tension is pulling up at the far edge of the yo-yo, right? Tension is T. I'm told that it has a radius R. That's something you can measure. Just get out some calipers or something, right? So R is a given, and the mass M is given. And so the weight acts at the center of it because it's a uniform object. A solid disk is what we're acting like it is. So I have my weight going straight down, my tension going straight up, and R is the radius. That's it. So if we want to solve, we go through the process, right? We got our free body diagram. Cool. Let's look at some of the forces, some of the torques. So some of the forces in the y direction equals ma. I left off some of the forces in the x direction because there aren't any. All right. If I'm calling up positive, you have t minus mg equals m times negative a. I know it's accelerating down. You could also define down as positive, and then you'd have mg minus t equals a positive ma. But that's just the same as this equation written just multiplied by -1, right? So I want tension and A. I have one equation with the same two unknowns. I can't solve. Got to move to somewhere else, but I'm going to leave this. It might come in handy later. Let's look at some of the torques. My axis of rotation, I'm going to call the center of my yo-yo because that's really the point about which it's spinning. This gets a little confusing because it's moving down and spinning at the same time, but that central point should still be the axis of rotation, although you can solve this multiple ways. So net torque equals I alpha. If this is my axis of rotation, the weight has no torque. The only torque is from my tension with the lever arm distance of R. So, okay. I also plugged in my I value first, I forgot. I for a solid disk. Oh, what is it? I'm not sure. Let's flip back. Boom. Solid disk isn't on here, but it's really just a skinny cylinder. If you notice the cylinder, it has no variable h. The height of the cylinder doesn't actually matter. Well, it does, right? It makes the thicker it is, the more mass it has. But in terms of the equation, it's not going to affect it other than through the mass. So a solid cylinder and a solid disk are the same. So the moment of inertia for my yo-yo is just 1/2 mr squared. And so my torque is T times R. I is 1/2 mr squared. And then I have alpha. But, oh bother, right? We still have tension that we don't know. We have A that we don't know. But now we've introduced alpha, another variable we don't know. So now we have 3 unknowns. What do we do? Oh boy, howdy. Well, if the yo-yo is unraveling off of this tension, right, then there's actually the linear acceleration downward of the yo-yo is the same as the tangential acceleration at this point, which is really like the acceleration as it comes off of the rope. And so then we can actually say that our linear acceleration A is just equal to alpha times R, or alpha just equals A, the linear acceleration, over R. Oh, sneaky. Now if I plug that in, now I have an equation that only depends on tension and A, just like my equation here, tension and A, 2 equations, 2 unknowns we can solve. There's a bunch of extra r's in here though, right? R squared over R, cancel out, 1r. TR, you can cancel an R on both sides. And look at this, oh boy howdy. The tension in the string reduces down to simply just being exactly equal to 1/2 the mass times acceleration of the yo-yo. That's neat. So now we can pop this in over here, right? So for T, I put in 1/2 ma minus the weight equals -ma. So do some algebra. I get 3/2 ma equals mg. My m's cancel. Pop the 3/2 to the other side as 2/3. And my acceleration is just 2/3 times the acceleration due to gravity. Plugging that back in over on this other side, I find that my tension is just equal to 1/3 the weight of the yo-yo. So it's accelerating downward at 2/3 the rate of gravity, less than what it normally would be because of the rotational motion, and the tension in the string is 1/3 the weight of the yo-yo. Pretty cool. Boxworthy. Oh, wow. Okay, 1 second. Please pause. All right, I paused and came back because I felt bad. My A didn't get a box around it. So there we go. Boxworthy. Acceleration is 2/3 times gravity, and the tension is 1/3 the weight. Pretty neat. All right, so one more example problem I want to do for you all, and then we'll call it quits on this video and wrap up Chapter 9 in the third video after this. So, yeah, I love bowling. I've always loved bowling. So you have a bowling ball that's coming down that little like return ramp thing that it sends it to you. Okay, so the bowling ball is going to be rolling down an incline, a ramp, and it's rolling without slipping. That's important because then you know tangential acceleration is the same as the acceleration of the center of mass. So we have a bowling ball, solid sphere of mass m, rolling down a ramp of angle beta. I'm doing a lot of variable stuff here because I want you to really see how this all works together. I want you to figure out what is the ball's acceleration down the ramp and what is the friction force acting on the ball. Why am I talking about friction? Well, if the ball's rolling down the ramp, there must be friction at the bottom causing it to rotate, right? And what type of friction? Well, it's a static force of friction that's causing it to rotate because it's rolling without slipping. Okay, so try this one out. Again, think forces, sums of the forces and sum of the torques, okay? Pause it and giddy up. All right, so here's the problem. Here's kind of a visualization of what's going on. You have a bowling ball accelerating down the ramp, and we're trying to find its acceleration as well as the friction force. So here's my free body diagram. Weight force going straight down, the normal force perpendicular to the ramp, and the static force of friction up the ramp. I rotated my axes to be perpendicular and parallel to my ramp, and I went ahead and took my weight force and broke it down into x components and y components. Okay, so let's try to solve. We're trying to find A and friction force. So sum of the forces in the x direction equals ma. Cool. So we go ahead and plug in. Let's see, in the positive x direction, which I'm calling down the ramp, I have mg sine beta. In the negative x direction, I have the friction. That's all. And that equals ma. Cool. I don't know friction and I don't know A. Two unknowns. Bummer. So let's look at some of the torques now. Notice I'm not even doing sum of the force in the y right now. I could. It'd tell me normal force equals mg cosine beta, but that's not necessary at present. So sum of the torques equals I alpha. Again, if you go back and check out that kind of diagram with all the different moments of inertia for different geometries, we find for a solid sphere it's 2/5 mr squared. Okay, and what is generating a torque? Well, first we need to identify our axis of rotation, which in this case should be the center of the ball. The weight and normal force both act at the center, so their torque is 0, and all is left is the friction force acting at a distance r away from the center. And that's a perpendicular lever arm distance, so my torque is just the friction times r, and that equals 2/5 mr squared, and then multiplied by your angular acceleration. The subscript z here, in case you're wondering why that's there, I'm just saying that it's axis, right? Because again, we define them in terms of direction about the axis which they're rotating. That axis is coming out of the page in the z direction. So alpha would be about that z direction. The torque is about that z direction. Now once again, since it's rolling without slipping, we know acceleration equals alpha times r, so we can use that by substituting in a over r for alpha, and we find that our force of friction is just 2/5 m r a over r, or 2/5 ma, 2/5 m times a. So our friction is 2/5 ma. That's cool. Now let's pop that into my other equation over here. So I have mg sine beta minus 2/5 ma for friction equals ma. Put those together, you get 7 over 5. 7/5 a equals g sine beta. The m's all cancel because every term has an m in it. All right. Solving for the acceleration, you find that the acceleration is just 5/7 g times the sine of the angle. Oh, that's neat. Boxworthy. Boom. You can then plug that back into the friction equation, right? 2/5 m times this a, which is 5/7. Oh, fun fractions. The 5's will cancel, and you find that the force of friction is 2/7 mg sine beta. Pretty crazy, right? But once again, boom, box worthy. All right, so that's again another example of how we use these forces and the the forces, the torques, and then the rotational motion ideas that we learned all together to solve these problems. So these really are going to give us a wide variety of different cool things we can do and solve, but it does get tricky and you got to stay really well organized, all right? So hope that helps. Hope you guys can dive in, and yeah, let me know if you have questions.